Hello, welcome to the C video course. For a number of years I worked for a C compiler vendor, in the early days in customer telephone support. During that time I spoke with many who were learning C, and it seemed all of these had difficulties grasping the same concepts, that everyone I spoke to tripped over the same hurdles. That experience I've tried to bring to this course. If it seems that there are one or two points that we seem to be repeating with regular monotony, that will be one of those places where there's often a problem. But enough about me. What about you? Well, we expect you to have a programming aptitude. We also expect you to know one end of a computer from the other. But what we don't expect is for you to have another programming language. If you do, so much the better. The concepts will be easier to grasp, but we're going to start from square one. Another thing that we do expect, though, is for you to work through the workbook. The video presentations are generally of a reasonable length, and there's a lot to digest after each one. But the tasks set in the workbook are not just designed to sound down the video material. They're designed to take you further, to test your understanding, to discover little wrinkles of the language that we don't cover in the video, and more than anything else, to experiment. By the same token, the workbook will be difficult to understand unless you first watch the video. The two are designed to work together. C is a powerful language. It's also a stepping stone towards C++. To understand C++, you first need to understand much of C. And most C++ tutorials still expect you already to understand C. So whether you're interested in C for its own sake or as a stepping stone to C++, this is where we begin. We begin with a paradox. A point that may be perfectly obvious to those of you with another programming language under your belt, but not necessarily so obvious to those of you new to programming. To understand this paradox, we need to look at a simple C program, one that simply prints the words "Hello World" onto a computer console. Written in C, this program looks something like this. This particular program is famous, you might even say infamous, as it's reputedly the first C program ever written. But it's not its history that is of concern to us now, nor its syntax. All we want you to notice about this program is that what we have is text. That C is text, something that we might write with a text editor or a word processor. So what? Well, the ironic thing is that this text program, written to control a computer, written in C, cannot be understood by a computer. Hang on a minute. We're writing a computer program that computers don't understand. Perhaps the reason why we might want to do this will become a little more obvious when you look at something that a computer does understand. Machine code. Wow. Complicated, isn't it? Can you imagine going into this maybe 6 months after you've finished an application and trying to work out what it does? Can you imagine trying to understand someone else's code? Can you imagine the errors or bugs that must be lurking around here and how difficult they're going to be to find? And last but not least is the fact that machine code is inherently non-portable. There can be profound differences even with a single architecture. for instance, the memory models on a PC. Never mind the differences that will arise as we decide to port from one machine to another, from a PC to a Macintosh, for instance. On the other hand, if we write in C, to a much greater extent our code will be portable. But we still have the paradox. A text program that a computer doesn't understand. Here, enter StageWrite, a computer program known as a compiler. The compiler takes as its source, in this case, C files, sometimes known as source files, and generates as its output what are known as object files, machine code. You notice also this set of files that we have here. These are header files. Well, what are header files? You'll soon come to appreciate that C programmers are terrible typists. They hate typing needlessly, and often in applications there is code that will appear in lots of different source files, and so instead of repeatedly typing the same code, we put that code into a header file, and then this header file gets inserted, pasted into each of the source files that requires that code. So, we have the compiler taking as its input C text files and generating as its output object files, machine code. So do we now have in our machine code something that a computer can execute? Unfortunately, the answer is no. We might think of the output of a compiler as being a bit like the rushes that we get at the end of a day's shooting of a motion picture. They're the raw material for the motion picture, but they're not the motion picture itself. There's an extra stage that needs to be gone through before we get the finished product. In a typical application, we'll have a number of source files. Each of these source files will go through the compiler, and so we will end up with a number of object files. Now, what do we do with these object files? Some we might store away into files called libraries. A library is a collection of object files. Many tasks are very common. Printing to the screen, inputting a character, joining two pieces of text together. These tasks, which are the sort of thing that we'll be wanting to do time and again, are often placed into a library. Then, next time we need to perform the task, rather than having to write the code again, rather than having to put it through the compiler again, we can simply extract the object code, the machine code to perform that task from the library. Okay, so where are we? What's still got to be done? We've got a number of pieces of object code, each of which is being compiled. We have more object code sitting in libraries that we may have built ourselves, or maybe we've bought. Using our motion picture analogy, the whole lot needs to be edited into some sort of order that makes sense. So what we end up with is not a collection of unrelated snippets of machine code, but an executable program with a beginning, a middle, and an end. This is a job for another computer program called a linker. Sometimes some systems a loader. The linker will link together the individual pieces of our program. It searches through libraries and extracts any necessary code from there, and then it links the whole lot together into an executable program, a program that will do something, that will control a computer. So that's our paradox. C programs cannot be understood by a computer. They first need to be compiled and linked. We now need to look at our simple C program, our Hello World program, to get a feel of some of the components that are in all C programs, some of the terms, the syntax, so that we can get a feel of the way in which C programs work. The first thing that we want you to notice is the top line that we have here. This is a comment. In C, comments start with a slash character, and note the direction in which the slash goes, and immediately following there is an asterisk, and they continue, the comment continues until we get to another asterisk slash combination. Now, because of the fact that the comment continues till we get to a final asterisk / combination, C comments can extend onto more than one line. But for the same reason, you can't nest comments. If your C editor, like this one does here, has syntax colouring, you'll notice the final asterisk / combination is in a different colour. It isn't part of the comment, and as it's invalid C syntax, a compiler will generate an error. It doesn't understand these final two characters. So, the next question, where does a C program start? Does it begin on the first line, or where? Put simply, C programs begin with a function called main. Now, before we can talk about main, we need to find out what a function is. What is a function? Simply described, a function is a piece of code, a series of instructions that has a name and can be executed by use of that name. So here we have a function with the name main. There's its name. You recognise that it's a function, that this is the name of a function, by the parenthesis that follows the name. The parentheses are a kind of trademark that identify a function. Notice too the curly braces. The instructions that are going to specify what this function does are contained between the two braces. So let's go back to our original program, and you'll notice that we have a function, main, with the parenthesis following, and then between the two braces we have the line printf hello world. This is the instruction that's going to print the words hello world onto the console. Being a very simple program, that's all this program does. Prints the two words and then terminates. So, having got a function, the question is, what do we do with it? How do we use it? We've defined it, we've said what it does, providing instructions between the two braces. Now what? Most C programs consist of more than one function. A C program can be thought of as a series of functions being executed. Here's another C program. But to show how functions work, we've coded it with 3 functions. You recognise them by the parenthesis following the names and the braces. We've also set the program up for debugging. Debuggers are a very useful tool for learning the C language. They allow us to do all kinds of things, and one of them that we're going to find very useful now is to step through our code line by line. So, where does this program begin? Remember, it begins with a function called main. So, watch what happens as we start to single step through the code. You notice that we began with main, and then we stepped down and came to what? Well, this is a function because you notice that we have a name followed by parenthesis. But instead of having braces following, there's just a semicolon. A complete C instruction is called a statement, and all statements end with a semicolon. It acts like the period at the end of a sentence, punctuates, separates one statement from another. So here we're using the function name differently. Rather than define the function, what we're actually doing is saying, go find the code for this function and execute it, run it. So, as you would expect, if we carry on single stepping, control jumps from here to the matching function, to the function with the same name, and we execute the instructions there, and then we return back to the following statement in our main function. Again, we recognise what we have here as being a function by the parenthesis that follow its name. So, again, if we single step in exactly the same way, we jump to the function that has the same name, and we execute the instructions in this function, and then we return back to main to the line following, and the program terminates. Here we've set up something very similar to our Hello World program. This time though, we've split the Hello World program into 2 functions. So watch what happens as again we single step through it. Our program begins at main, and it goes down to the function call print hello world. We jump to that function, execute the instructions there in the process, printing hello world onto the monitor, back to main, to the instruction following the function call, and the program terminates. For functions to be able to do their jobs properly, we generally need to communicate with them. Now, what do I mean by communication? Well, the first thing is communication is two-way. I know people that have wonderful conversations with trees and flowers, but I venture to suggest that they don't actually communicate with those trees and flowers because they don't talk back. So, to be able to communicate with our functions, we first of all need to tell them what to do. And this is done by providing information in the parenthesis. We needed to tell printf what to do, what to print on the display. And this was done by providing text within the parentheses. Suppose we have a function called function, and we need to give it the value 100. need to pass that information to this function so that it can do a particular job. Well, we put that value 100 in the parenthesis. Some functions don't need any further information. They just need to be told to go, to do their thing, to do their job. A function, for instance, to clear the screen, clear the console, can just go and do so without any further information. On the other hand, a function such as this one, add two numbers, presumably needs to know which two numbers it should add together. So you notice that we have two pieces of information, a 4 and a 5, and they are separated by a comma. The various pieces of information that we give to a function are known as its arguments, and the arguments are separated by commas. So printf, the function that we have here, has one argument, the text that goes between its parentheses. But hang on a minute, where's the code for printf? After all, in all the other examples we looked at, when we called a function, we could see clearly in our program where control was going, because we jumped to that function, a function with the same name. But here in our simple C program, our Hello World program, there is no code for printf. The answer is that the code for printf is contained in a library. It's a very common task to want to print something onto the display. Exactly the sort of thing that you would expect to find in a library. In fact, the task is so common that printf is what is called a standard library function. The standard library is a library that is supplied with all C compilers. Whichever compiler you are using, you can expect there to be a printf function. In fact, all the functions that we'll be introducing you to in this course will be standard library functions unless we state otherwise. So the linker will notice the call to printf and that you've not supplied a definition for it, you've not stated in the Hello World program what printf does. So it will look in the standard library, it will find the machine code for the printf function there, and that code will be extracted and inserted into what will become your executable. Now, normally, linkers will search the standard library automatically for any functions you haven't supplied definitions for. However, again, normally, you need to tell the linker specifically somehow about other libraries you may have built or own. Precise details as to how you do this will be in the notes for your linker, and these vary from system to system. We said that communication is two-way. Not only do we have to tell the function what to do, but after it's done it, it has to tell us what it's done. It has to tell us what it's accomplished. And this is accomplished using the return keyword. We can return a value such as 0, 5, -5 from a program. Look again at our Hello World program. We return a value of 0 back to the operating system. In C, 0 is often used to signify success and non-zero to signify failure. We're telling the operating system that as far as we're concerned, our program has succeeded and it's not to generate any errors. If we call a function, how can we determine what has been returned? Look at this piece of code. Add two numbers. We're adding together two numbers, the two numbers 4 and 5. But how do we use the answer? In ordinary code, if we weren't using the function, we would say something like this: x equals 4 plus 5. Using a function is exactly the same. We can say x equals add two numbers 4, 5. Here's the information that we give to the function, and the function is presumably going to return the value of 9 back to us, and that's what becomes the value of this expression, the value of the function that appears here, and it's that is assigned to x. There's one line of our program that we haven't yet explained. This one here. It begins with this character, variously called a pound sign or a hash sign, depending on where you come from in the world. But it always has the same meaning. Lines that begin with this character are to be processed by what is called the preprocessor. What is a preprocessor? It's a kind of front end to the compiler. It does some textual manipulation, things like macro substitution on the file before the compiler itself gets a look in. The include preprocessor command is an instruction for the preprocessor to include, paste the contents of another file at this point, at the point of the include command. And the file that's going to be pasted at this point is a file called standardio.h. It's a header file. You remember, we spoke about these earlier. Code that we don't want to keep typing over and over again goes in a header file. So this program only looks 7 or 8 lines long, but the compiler, depending on the length of standardio.h, could actually get to see a program 200 to 300 lines long, assuming that's the kind of length of standardio.h. These 200 to 300 or so lines are called a translation unit. It's that the compiler actually gets to process. So why paste standardio.h into our simple C program? The reason is because standardio.h contains the prototype for the function printf. A prototype is information about how a function is to be used, such as the number and the type of the arguments that the function is expecting. Printf here is expecting some text. It's going to print that text onto the display. But supposing we call printf and we didn't give it any arguments, no information at all as to what to print. Now, we know that doesn't make sense, but the compiler doesn't know that, not unless we provide a prototype. If we provide a prototype and use printf then without any arguments, the compiler would generate an error to the effect that we've used printf incorrectly. And that's extremely valuable information because it saves us having to spend hours searching through loads of code later when the program doesn't work without us having any real inkling as to why it doesn't work. Prototypes are not compulsory. You don't have to prototype functions that you write, but you're stupid if you don't. And we'll be showing you how to prototype the functions you write as soon as possible. In the meantime, you'll be confined to prototyping the standard functions. There are 15 standard headers containing the prototypes for the standard library. And each time we introduce you to a function, we'll mention the file you'll need to include that contains its prototype. The prototype for printf is contained in standard.io.h. At this point, we would like you to go and do the tasks associated with this unit. Let me give you some encouragement by going over one or two tasks associated with this unit to show you why it's important for you to do so. We've looked at some depth at this Hello World program. But one of the things that we haven't done is show you what this \n does. So we'd like you to go and experiment with it to see if you can find out what it does. One of the ways you can do that is by moving the /n to the middle of the text. Now, while you're doing that, you might also try experimenting with a /0. Now, we don't mean the letter 0, but the digit 0. Okay? Or what about a /t, a /r, or a /b? What effect do these have when we put them within the text? Also, it will be good to experiment with the effect of white space. What happens, for instance, if we split the line here and put our preprocessor line onto two lines? Can we get away with that? Or what if we split the line here on our main line, if we put the parenthesis on a different line to the function name? And what about here within the text? Supposing we put the world on a separate line from hello. Does that have any effect? Does it make any difference? These exercises, the things that we ask you to do and that are in the workbook, are not just a rehash of what we're discussing, but are designed to take you further than the video material. Now, as we're trying to break you in gently, we'll come back next time and talk about what you've done and what you should have discovered.